this section, we're going to look at the relationship between graphs of f and f inverse. Before we start looking at the topic here, let's talk about a new notation. You'll see this looks like an f with a little -1 to the top right. We use that notation instead of writing out the word inverse. So instead of writing f inverse, we do f with a little -1 in the upper right hand corner. But those two things mean the same thing. And this is how we're going to write f inverse now, f with a little -1 to the top right. Our goal in this section is to compare the original graph of f with its inverse function and to see how do we graph its inverse function. So the first thing I'm going to do is I'm going to look at this blue graph here on this example, and we're going to call this graph f. So we're going to look at just the blue graph. I'm going to label some points. So here's my x-axis. Just going to label some values on that axis. And then we're going to label some values on our y-axis. Okay, and what I'm going to do is I'm just going to pick off some ordered pairs that live on this graph. You can pick out as many or as few as you wish, but I'm just going to pick out about 4 or 5 and just look at some of the features of this blue graph f. So I'm going to pick out a point. This point right here looks like it has an x value of 2 and a y value of 5. I'm just going to make a list over here of these ordered pairs that I find on the graph of f. Let's look at the y-intercept. It's not exact, but we can guess. Looks like 0 for x and a y value of about 3.8. Doesn't have to be perfect. We're just trying to pick off what we can tell in a very general way. Okay, the next nice one looks like it's about, what is that, about -3 for x and a y value of 2. And I'm going to pick up my x-intercept. My x-intercept looks like it's about -3.8. and the y value of an x-intercept is 0. And this point down here looks like an x value of -5 and a y value also of -5. I'm just going to put this on my list. Okay, so there's the graph of f. Let's also come up with our domain and range for f. So we're basically just trying to describe as much as we know about this original function f that we're given. Alright, the domain. Remember, we're going from left to right, x values. So the x value on the very left looks like a -5. It's included on my graph as a closed circle, so I'll put a bracket next to it to mean included. Then we're going to go all the way to the rightmost point, and we're going to find the x value of that point, and that's 2. Also a closed filled-in circle on my graph, so I'm going to put a closed bracket next to the 2. For the range we do y values from bottom to top. So the y value at the very bottom is -5. It's also included on my graph, so I'm going to put a closed bracket. All the way at the top, the y value is a +5. Also included on our graph is a closed circle, so I'll put a closed bracket next to the 5 to say that y value is included. Now the point of this particular lesson is that if I can find a bunch of information out about f, as far as also all the ordered pairs, then I am able to graph f inverse very easily. First of all, how do I know that f has an inverse function to begin with? How do I know that f has an inverse function? Well, when I look at the graph of f, I see that it passes the horizontal line test. Any horizontal line that I could imagine drawing is only going to cross through the graph once. So it passes the horizontal line test and has an inverse function. I want to graph that inverse function. To graph the inverse function, all that this rule says here is that all I have to do is switch the x and y values in the ordered pair. So if I have 2, 5 on the original graph of f, a point on the inverse function will be 5, 2. So notice that I'm just moving the x and y values and I'm just switching them. I am not changing the signs of either one of them, we're just switching the location of the x's and the y's. So it looks like the ordered pair gets reversed. The next one would be 3.80, 2, -3. So notice here as well, I did not change the sign of the -3. It is still a -3. Instead of being in the front, now the -3 is just in the back. The +2 is in the back here. Now instead of being in the back, it's going to be moved to the front, but still a +2. The next point would be 0, -3.8. And then this one, it's okay that the x and y values happen to be the same, because when we switch them, that looks like nothing changed. That's okay. Sometimes those x and y values match, and then when we switch them, it looks like we didn't do anything, but officially we are switching those x and y values. Let's plot these points. 5, 2, 3.8, 0, 2, -3, see 0, about -3.8, and then -5, -5. And that point happens to be plotted right on top of one of the points for f, and that's okay. So I'm just going to connect my points from left to right. There we go. So this is the graph of our inverse function f. You'll notice that f inverse passes the vertical line test and has no repeated x's. So this has no repeated x's because this one has no repeated y's. What is the domain and range of our inverse function? Okay, so let's look at the domain. The domain of the red graph, we're going to look at the x value on the very left. It's -5, included, because it's closed, filled in circle. Then we're going to go all the way to the point on the very right, and we're going to pick off the x value there, which is a +5. Now we're going to move to the range. The range says we go from bottom to top. The bottommost y value is -5. The topmost y value is a +2. What we want to observe here is that the domain of the original function matches the range of the inverse function. So all we have to do, if I want to find the domain and range of the inverse function, is to copy and paste the domain from the original function to be the range of the inverse function. If I want to know the domain of the inverse function, all I have to do is go back to the range of the original, copy, paste, and that becomes the domain of my inverse function. The domain of the original is going to match the range of the inverse. The range of the original is going to match the domain of the inverse. So the domain and ranges switch. It's a copy and paste. Notice that we didn't move anything around. We just took -5 to 2, copied that, pasted that. Over here, the domain of the original, copy and pasted, it becomes the range of the inverse. Same thing for the original range. The original range, -5 to 5, copy that, paste that as the domain of the inverse. So the domain and ranges switch. It's a copy and paste situation for the domain and range of the inverse and its original function. Okay. One last thing that I do want to mention before we move on is that if you go to the origin 0, 0 and you draw a line kind of cutting diagonally through all those boxes, going straight at about a 45-degree angle, going all the way through, this is the line y equals x. This is a line where if you look at all the ordered pairs on that line, all the x's and y values would match each other. They would look exactly the same. The point -5, -5 is on that line. What you're going to notice is symmetry. Sometimes we call this the line of symmetry. So when you look at the original graph f and the graph of f inverse, one helpful thing to see did I graph them correctly is to look at a line of symmetry, the line y equals x. You'll notice that the graphs are like the mirror images of each other through that line y equals x. So you start at 0, 0, and you go up to 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, and so on, and go backwards -1, -1, -2, -2, kind of where all the x and y values match. You draw that line, and the graph of f and the graph of f inverse should be symmetrical to each other. Now, I'm not going to make you do much with that, but I do want you to observe that that is true, and that can help you as a little test to see did I graph those two correctly. Alright, let's look at another example. Alright, here we have the graph of f, and once again I'm going to just go ahead and do that in blue. So I'm going to label that f. F is a function. It's also a one-to-one function because it passes, again, the horizontal line test. So we know that it will have an inverse function. So our goal in this section is to graph the inverse function. So we're going to find some points for f, and then we're going to switch the order of the x and y values. So first we need to come up with some points that live on the graph of f, the original graph that we're given. So let's pick out a few points. So it looks like here we have -2, 3. Pick out some nice ones if we can. Looks like this point would be -1, is that 4? Okay, just guess to the best of your ability what that point would be. The next kind of nice one looks like 2, 5. And it looks like the next nice one has an x value of 7 and a y value of 6. And it looks like my graph continues to go to the right forever because of that arrow. So I'm just going to copy down a few of the points that I've already labeled. Okay, let's also come up with the domain and range. Okay, looks like the domain would be x value on the left would be -2, including -2, that's a closed filled in circle. Now when I go all the way to the right, I have an arrow, so that means infinity. Alright, the range would be bottommost y value, which would be 3, and it's included. When I go to the very top of the graph, once again I see an arrow, so we'll put infinity. My goal is to graph f inverse, the inverse function. So I'm going to use f with a little -1. All I have to do is switch the location of the x and y values in all of the ordered pairs. So that becomes 3, -2, 4, -1, 5, 2, and then 6, 7. So the x and y values are going to switch places. Now, here's something that I want to mention before we plot those points. Don't we already know the domain and range of the inverse function? So let's just do this and then we'll check it with our graph. We know what the domain of the inverse function is going to be before we even graph it. So let's just go ahead and write it. The domain of the inverse function will match exactly the range of the original. Copy and paste. The range of the inverse function will match the domain of the original. So just copy it and paste it. So I'm going to go ahead and put that as my domain and range for the inverse function, and then we'll come back and check it and make sure it's correct by looking at our graph. Alright, so let's go ahead and now plot those points. We have 3, negative 2. We have 4, negative 1. 5, 2. And it looks like we have 6, 7. Just going to connect those. Now, if I've graphed it correctly, the domain and range should be correct. So if I've done everything correctly, the domain and range that I've written down should describe the graph of f inverse. So let's double check. On the leftmost x value is 3. So from left, we have an x value of 3. There we go. That makes sense. And when I go all the way to the very rightmost point of my graph, I see an arrow. So that would give me infinity. So the domain is correct for our inverse function. Okay, what about our range? Okay, if I go to the very bottom point should be negative 2. The y value of the very bottom point should be a negative 2. And it is. When I go all the way to the very top of the graph, I see an arrow, so that gives me infinity. So my domain and range are correct with what I knew they were supposed to be. Alright, let's do one more. Here we're asked to find the graph of the inverse function of f of x equals x cubed minus 4. So this time I'm actually telling you what that graph is, or what that function is. One of the things that I wanted to remind us of is this is one of our basic shape functions. And you should go back and look at transformations. I know it's been a little while since we talked about transformations, but we want to make sure that we remember, and in your homework you'll be asked to do this as well. We want to remember that we have our basic shape x cubed, and we have a negative 4 subtracted on the outside. So I want to remember that if we have an outside change, if we're adding or subtracting a number on the outside, it'll shift in the direction of the sign. It'll shift that origin point, in this case, down 4 units. Our basic shape was that cube function. Now you may be asked in your homework to recognize that basic shape from the equation and how it shifted. Here I've already graphed that for us. Here is our cube function, and the original origin point would have been 0, 0, and I've shifted that origin point down to negative 4. And my graph is that right side up cube function. I'm going to make this a little bit smaller here. Okay. So what we're asked to do is we're asked to graph the inverse function. So that's the original function, passes the horizontal line test, so now we want to graph the inverse. So let's find some points on the original graph of f. We've got 0, negative 4. Just find ones that look like they're nice little points at the corners. What we have over here is that 1, negative 3. So we're going to find them, label them. What else have we got? Maybe it looks like this point. Is that 2, 4? Yeah. Looks like this point's nice. Negative 1, negative 5. And that might be it. Okay. So let's make a list. We have 2, 4. 1, negative 3. 0, negative 4. Negative 1, negative 5. Domain and range. From left to right, arrows. Arrows at the very left, arrows at the very right, negative infinity to positive infinity. The range. The bottom, arrow, top, arrow. Once again, negative infinity to positive infinity. Now our goal is to take this one-to-one function f that passes the horizontal line test, and we want to graph f inverse. So I'm going to look at everything I have here, all my ordered pairs, and we're just going to reverse the x and y values of all the ordered pairs. So we have 4, 2, negative 3, positive 1, negative 4, 0, negative 5, negative 1. Let's plot those points. 4, 2. There we go. Is that negative 3, 1? Negative 4, 0. Negative 5, negative 1. And it looks like we have something that looks like this. Domain and range should be switched. So the domain of the inverse will match the range of the original. The range of the inverse will match the domain of the original. So when we look at our graph, we should have arrows at the left and the right, and arrows at the top and the bottom of the graph. And we do. Something else we want to notice, and we'll go back and do this for the last graph as well, is we do have that symmetry. If I go back to the origin and I start crossing through, drawing a line that crosses through all those points that have the same x and the same y, I do see that symmetry. So that line y equals x is that line of symmetry. And we see that the graphs look like the mirror image of each other through that line. Something else that's interesting to observe is the original function that we had was that cube function. That was one of our basic shapes. Does the red graph look kind of familiar to you? And hopefully it does. That red graph should actually look like the cube root function. This is another one of our basic shapes. This will always be true. If you start out with a cube function, your inverse function will be the cube root function. That's what that picture will look like. It looks to me like the cube root function got shifted to the left 4 units. So let's just make a quick little guess as to what that equation would look like. If I shift that graph to the left, that would be adding, right, on the inside? If we go back to our function transformations, wouldn't that be the cube root with that radical symbol of x plus 4? Remember, adding on the inside would shift the graph to the left 4 units. So you don't have to do that, but that was just a guess and a little nice observation to make for what that graph could be. Alright, let's go back and just take a peek at our last graph and verify that it does have that line of symmetry. So when I start at 0, 0 at the origin, and I go to 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8, 8, and so on. And I do the same thing in the other direction. I see that the graph the two graphs are symmetric with each other through that line y equals x. So just another verification that we drew those graphs correctly.